So today we will be talking about using the ideal gas laws with a closed system. So we have this closed system that has air in it, and then we have a little bit of water down here in the bottom. So originally we don't have a top on our system, but we're going to put a top on the system to make it a completely closed system, and then we're going to have to figure out at what pressure or at what temperature are we going to reach a pressure of 200,000 pascals. So to start off, we are going to start talking about the different partial pressures of what is inside our system. So we are going to have the pressure total is going to equal the partial pressure of our water, which actually, last video, we made a Python code using Antoine's equation to find the partial pressure of water. So today in this video, we are going to use that Python code to find the partial pressure of water. I'm so sorry. So this is going to be Antoine's equation. And then we are going to have to add the partial pressure of air. So today we are going to be mostly focusing on the partial pressure of air. So to start finding the partial pressure of air, we're going to first start off with the ideal gas law, which is PV equals nRT. So to find the pressure of our system, we are going to take and we are going to have the pressure is equal to nRT divided by V. So now we must find the volume of the vapor phase. So the volume of the vapor phase is the denominator for the partial pressure of our air. So for the volume of the vapor, we have this closed system, and in our closed system there's three volumes. We have the volume of our vapor, we have the volume of our water, and those two add up to get our volume total. So we don't know our volume of vapor, so we need to solve for that. And we know the volume total, so we're going to have the volume of the vapor equals volume total plus the volume of the water. So we know the volume total is 0.1 meters cubed. We already know that. That's given to us. So now we must find the volume of the water. We don't know the volume of the water, but we know the mass of the water. So we are going to have, and we also know the density of water. So we are going to take the density of water, and it is going to be equal to the mass of the water divided by the volume of the water. So we can rearrange this equation and we can get the volume of water is equal to the mass of water divided by the density of water. So we are going to have 1 kilogram divided by 10 to the third kilograms per meter cubed. Alright, so now we are going to go and we are going to write all of this into one equation. So we are going to have P water plus P air. Those are our partial pressures of water and our partial pressure of air. So this is going to be set equal to the number of moles times R times the initial temperature. And this is going to be divided by V total plus V water. So now we want to solve this equation for our moles. So we are going to have P water plus P air times V total plus VW, V water, and this is going to be divided by R times TI, and we are going to set this equal to N. Alright, so we are going to start off in Colab. So we are going to look at our GitHub site. So we are going to go into our section of this class, and then we are going to go to closed water, air, in class. So this is a code of everything that we are about to do. So I will show you how this works. So we are going to copy and paste this first line here. So all this is going to do is give us all of these files in here. So when you open up files, you're going to come to this CHE tools, and we are going to be able to see all of these codes that are pre-written for us. So we will use che.py the most. So this is just a long code that we are able to use. So now if we go into data, we can look at, we have all of these different compounds and all of the properties of these different compounds. So if we go to water, we can see that we have the critical temperature, pressure, volume, melting point. We have a bunch of different properties of water written in here, so we can just pull them straight from there, and we don't have to type them in ourselves and accidentally make a mistake. So we are going to go back to our GitHub site, and we are also going to copy and paste the import sys. So this is just a pathway to the CHE model import. So actually, I want to put this up here. We're going to hit Shift Enter. So now we have access to all of those. So now we are also going to import this che.tools as CHE. So now all we have to do is type in CHE instead of typing out tools.che. Oh. I typed this backwards. It is tools.che. So we're going to hit Shift Enter, and now we can use that CHE as tools.che. So now we can use all of those properties inside CHE. So if we do P equals CHE dot props of water, now we are able to pull all of those properties of water and use them. So if we do P dot, this will show you all of the different programs that we can use. So we can see here we have, down here we have the row of liquid, which is the density. We have the pressure of the vapor. We have all these fun programs that we can use. So we are going to use P vapor. And if we type in 370, it'll give us a value for that. So that's around 100,000. And then we can also do P dot row. And we can do that of about 300. And that's going to give us around 1,000. So if we go up here and we add in some more compounds, we can add in ethane. How about toluene, and how about one more? Let's do nitrogen. So if we do that and we hit Shift Enter, and we can come down here, and this will give us the densities of our compounds now. So this is water, then we have ethane, then we have toluene, and even if we go back up here and hit Shift Enter again, it'll give us all of these. So the first one's water, second one's ethane, third one is toluene, and the fourth one is nitrogen. So now we are going to start working on our nonlinear equation. So if we go up here, we have to import SciPy. So we do a SciPy dot optimize import root. So SciPy can give us the root of a vector function. All we have to do is make an initial guess. So while we are up here, we are going to also initialize r as 8.314. So that is just a constant value. And hit Shift Enter. We're going to go down here and we are actually going to delete these. We don't need these anymore. So now we are going to start initializing all of our values for our specific problem. So we're going to have V total equals 0.1, and this is meters cubed. We are going to have the water mass, which is equal to 1. So this is kilograms. And we're going to have the initial pressure equal to atmospheric pressure. This is in pascals. And then the final pressure that we are looking for is 200,000. So this is also in pascals. And then we are also going to initialize our initial temperature, and that is 298 Kelvin. So we are going to go back up here, and we are just going to change this back to water, since water is the only compound that we care about. So now we are going to go back to our whiteboard for a second. All right, so now we are going to type that equation that we just wrote into Colab. So first, let's figure out what the density of water at our initial temperature is going to be. So if we hit Shift Enter, so the initial, or our density at our initial temperature, so our initial temperature is 298 degrees Kelvin. So our density at that temperature is going to be 995. So now we want to type in that equation that we just wrote on our whiteboard. So we are going to have the moles of air equal to the initial pressure minus the P dot vape, that P vape time of the initial temperature. So now we're going to go out and we are going to multiply this by V total minus the water mass divided by rho, P dot rho of our initial temperature. And then we're going to divide all of this by R times the initial temperature. So we're going to hit Shift Enter, and then if we type in air and Shift Enter, that is going to be that is the amount of moles inside of our closed system. So now we know how to find the partial pressure of air. So now we are going to go back to this equation and we are going to plug in the partial pressure of air. So we are going to have P total is equal to P water plus we're going to have N R Ti over V vapor. And we know that this V vapor is V total plus V water. So now if we set this entire equation equal to 0, we're going to be able to find the roots of the equation. Okay, so now we are going to solve for the pressure. So we are going to have the equation for pressure, and we are going to make this a vector. We need to define this. All right, so we are going to have temperature final is equal to the vector equal to 0. So now we are going to have our V vapor equal to the V total minus the water mass divided by the density of T initial, our initial temperature. And then we are going to have our water pressure, or partial pressure for water equal to P dot P vape of our final temperature. And then we are going to have, put that parenthesis back up there. And then we are going to have our partial pressure of our air equal to the moles of air times R times times R times the final temperature divided by V vapor. So now we are going to return our partial pressure of water plus the partial pressure of air minus the final pressure. We're going to set this equal to 0. Nope, we don't need to set that equal to 0. So the only problem I had here, this is not a capital R, it is a lowercase r. So now that last line is going to come out as 0. So if we do the roots of the pressure equation, EQUAT, and then we have our initial temperature as our initial guess, then we can see that our function equals 0, so that the partial pressure of water plus the partial pressure of the air minus the partial pressure of the entire system is going to be equal to 0. So that does make sense because it's what we have inside added together minus our entire system. So then we can also see down here that our array is going to be our final temperature. So now we are going to say that our moles, so this is a new problem we have, now we want our desired number of moles to be 0.3. So we are going to initialize that our desired moles is going to be equal to 0.3. And now we can copy and paste all of this. We can copy and paste this down here. And we are going to change this to P equate 2, since it's our second equation. And we also have to change the V of vapor. And we have to take this and we have to change this to the desired moles. DESIRED. And we are going to multiply this by P dot MW, which is the molecular weight, and we are going to divide it by 1E3. And we are going to keep that last part of the equation the same. We're going to hit Shift Enter. Oh, nope, we need to go back in and we need to do, we need to add down here a P air underscore NWV is equal to the partial pressure of water times the V of the vapor divided by R times the final temperature. And now we are going to return PW plus P air minus PF. And we're going to do comma NWR minus NWV, not R, I'm sorry. And then we're going to have NWV underscore desired. Let's put brackets around this and then Shift Enter. Okay, so we have some invalid syntax. I believe this is backwards. Let's try that again. We do not need this P air out in front. This is just the NWV. So we initialize that value. So now we are going to return and we are going to take the root of P equate 2. And we are going to have our initial temperature, and our initial guess is going to be around 0.01. So we're going to shift enter. So we had some invalid syntax there, but we finally got there. So now we are going to go in here and we are going to change our initial temperature to 360. I think that's going to be a better guess for us. Okay, so I've gone back through our code here and realized that we did not initialize our final V total. So we need to have this as a vector of 1. And we also did not put in our n-air equation, so we need to type in our n-air equation here. So we have pi minus p dot p vape of our initial temperature, and then we have times our total volume minus the water mass divided by p dot rho of our initial temperature. And then we also need to divide this whole thing by R times our initial temperature. So now, okay, so now we can see that our equation, or our solution, converged at 370 degrees Kelvin. So if we go back here and look at our code, we can see that our final temperature was 370 degrees. But if we look at this piece right here, this is our final volume. And obviously having a negative final volume does not make any sense. So if we go back into our Colab and we look at this, in our previous attempt, we did not put this the mass of the water, we did not put that in our V vapor equation, so the mass of the water needs to be put in there because we have to have the V vapor equal to V total minus the water mass minus the desired moles times the molecular weight of water divided by 1 times 10 to the third, and then we have to divide that by the density of our final, or our initial, we have to divide that by the rho, which is our density of our initial temperature. So if we are to rerun all of this, we can now see that our final temperature changed by just a little bit, but it's still around 370 degrees. And then we can now see that our final volume is 0.001, but we can now see that we have a positive value now, so this does make sense for our problem. So this video shows me solving 2 problems dealing with the ideal gas laws within a closed system. Thank you for watching.